excuse me, our very first chapter 15 quiz. You hopefully see this as chapter 15 quiz 1. Let me know if you don't, because if you don't, it just means I made a mistake somewhere. So this is a brand new application. This is simple harmonic motion, simple harmonic motion. And here's the trigger for everything. Simple harmonic motion is what happens when you have a restorative linear force. So this is the trigger for everything that we're going to deal with in chapter 15. Simple harmonic motion is fundamental to automotive suspensions, quantum mechanics, pendulums, electrical engineering. It's a very far-reaching topic, and it all comes from this. Whenever you have a force that can be sort of put into this form, and this is Hooke's law. So this is the form we've seen for a simple spring. And you could say to yourself, well, okay, as long as I'm dealing with simple springs, I guess I'm good to go. But how interesting are simple springs? But the response is, it turns out a lot of complicated phenomena can be boiled down into an expression pretty much like this, that go well beyond simple springs. Again, electrical engineering, automotive suspension, quantum mechanics, and other things I'm not even remembering. But if you say, well, okay, this is one of my forces, and I'm going to do the force analysis method, which means an X force inventory or a Y force inventory. And I'm going to say, well, the sum of all the X forces equals, if you just standard operating procedure, and now you realize, well, there's another force that's reared its ugly head called this kind of restorative force. This negative sign means springs always want to go home. If you compress a spring, what does the spring want to do? It wants to elongate. If you elongate a spring, the spring wants to compress. A spring always wants to go home. It always opposes what you try to do to it. That's the purpose of the negative sign. The linear relationship between force has to do with the fact that it's X to a power of 1. So, for example, if I had a force like this, this would not be linear related. This would be a direct square relationship, this is a whole nother path to go down. But anyway, this is the air we're breathing. Simple harmonic motion. Everything is the same in terms of fundamental approaches. So we know we're smart about kinematics analysis method, force analysis method, energy analysis method, and we're just going to stick to our guns, and we're going to say, okay, let's just keep doing the same thing, all this chapter 1 through 8 stuff. And now we're just going to really kind of drill down on situations that involve this magical restorative force. Okay, so here's our first problem. We have block 2 here, bouncing back and forth on this table. Block 1 has a mass, it's sliding to the right. So as block 1 is heading to the right, block 2 is sitting there bouncing back and forth. So block 2 is just going, back and forth over and over again, because it's attached to a spring and there's no friction. So block 2 is just oscillating back and forth, undergoing simple harmonic motion. So we would refer to block 2 as a simple harmonic oscillator. The block undergoes an elastic collision with a stationary block 2. Oh, so I guess block 2 is bouncing back and forth only after the collision happens. So a little clarification there. Okay, we know the K value we know the stiffness constant for the spring after the collision. So after the collision happens, block 2 is bouncing back and forth according to simple harmonic motion. So this is where I should say block 2 at this point is a simple harmonic oscillator, and it has a period of 0.12 seconds. All right, block 1 slides off the table. So the question is, if all of this is true, what's this? There's the dollar sign. Where does block 1 land? All right, so step number one is, I'm thinking impulse momentum theorem. I'm thinking J equals integral of F dt equals delta. Why am I thinking about this? Because this is the impulse momentum theorem, and there is a collision that's going on here. So impulse momentum theorem is what we use to analyze collisions. We had a whole lab on this. And you might say, well, why don't I just use force analysis? And the answer is impulse momentum is more expeditious to a collision compared to force analysis because you typically don't have a force sensor hooked up. Otherwise, you could take that approach. So I'm thinking of this. This is the first thing that comes to mind is block 2 is sitting here stationary. So this is a stationary target. And then there's a collision between block 1 and block 2. It says block 2, it's an elastic collision. So you remember the types of collision. There's elastic, there's inelastic, and then there's partially elastic, the intermediate, partially elastic. So these are the 3 types of collisions. We're dealing with an elastic collision. All right, so what am I going to do about that? Well, I want to find out the velocity of block 1 because block 1 is going to smash into block 2 and then bounce off block 2 and go flying off the tabletop over here. So I guess I want to find out the velocity of block 1 after that collision. So this is a job, again, for momentum. So for this is from chapter 9, for a one-dimensional elastic collision, this was derived for you. Momentum is conserved, kinetic energy is conserved, and then we did a bunch of algebra, and we found out this right here. Maybe I can do that right. This is the relationship that got spit out when we remembered that in any collision, momentum is conserved. And even better, if it's a elastic collision, kinetic energy is conserved. And this is what we can surmise when those two things, when we work with those two conservations, kinetic energy and momentum. All right. So right now I am after this right here. I'm after the velocity of block 1 after the impact. And then I can use that for kinematics. Okay. So let's go ahead and run with that. Here goes. Number 3. All right, V1 final, the velocity of block 1 after the collision is going to equal M1. Do I have M1? Yeah, it's 0.220 kg. The mass of block 1 has a mass of 0.22 kg minus M2. What's the mass of M2? And then I guess I'm going to have to say, I don't know M2. So you know what? Minus M2 over M1 plus M2. So things were going very plug and play. V1 initial is 7.55 meters per second. That's my number. 7.55 meters per second. So what's M2? Dead end. I'm officially at a dead end. And this is where you play the role of a detective. The great thing about being an engineer, you have to be logical and imaginative, all in the constraints of one single head. So what's M2? I guess I'm thinking, let's take a look at simple harmonic motion. Look at simple harmonic motion. So simple harmonic motion based, let me get to the lecture notes. Here they are. All right, so simple harmonic motion. It starts with that restorative force. So here's a whole bunch of stuff. Here are your lecture notes. Simple harmonic motion, lots to talk about, but I'm going to, I guess, go right to this page here. Okay. All right. Let's draw a spring mass system. So basically, I'm not going to go through this whole thing, but your lecture video does. Your lecture video says, hey, if we have a block sitting on a table and it's attached to a spring, this is M for mass. This is a spring stiffness constant. This is referred to as a spring mass system because it involves a spring and a mass, and it exhibits simple harmonic motion. And if we just say, well, let's do the force analysis method. Well, okay, I have my spring force going this way, and there's no friction, so I guess that's it. So I have my spring force is just going to equal mass times acceleration, and then we use the calculus version of acceleration, and we just keep going, d squared x dt squared. So it's
I can only see the notes still, not the actual quiz.
Yeah, your green sheet's Word doc is still up on your screen.
Here, okay. So thank you. Well, it's okay. It's okay. You didn't miss much because all I'm saying is what I said before. I'm saying here's a spring mass system. So let me repeat that. M stands for mass. K refers to the stiffness constant of the spring. We refer to this as a spring mass system. It's an example of a simple harmonic oscillator. What are other examples of a simple harmonic oscillator? A Ferris wheel at Cedar Point is an example of a simple harmonic oscillator. So is a pendulum. So is an RC circuit. So is a bunch of other stuff that we'll get it. So is a what chapter was that? So is an oscillating charge, and the list goes on. So this is what I was doing during the blackout. I was saying, hey, let's just do force analysis. I've got my spring force acting to the left. If this is moving to the right, then I'm just going to do my X force inventory. Anyway, that's what you see here. That's what you have lived through in these 5 boxes. Let's do the force analysis. Here's the X force inventory. Here's me doing the calculus version of acceleration here. So this is the X force inventory. This is the X force inventory with the calculus expression for acceleration, and I'm dividing through by M, and voila, we get to number 5. We get to number 5, which is a second order ordinary homogeneous differential equation. And this is, I think this might be the first time in this class where I actually have to say, I didn't have to say it here. I said, well, if I have this equation, what the heck is X? What's the solution to that equation? And before I get to that, if I have that equation, which I need to talk about, check out, this is a very important little teeny tiny note, which let me make this a little bit more dramatic in its appearance, because this is a very central assignment. This is a very central definition. Maybe I should say it's definitional. Okay, so what you see here, omega squared equals K over M. So before I go on, I just want to say that during this force analysis, and it really is a straight up generic force analysis, it turns out that that when I have K over M, so in step number 3, here's K, the spring stiffness constant. Here's M, the mass of the oscillator. And then I divide through by M, as I said, and I have K over M. So K over M turns out to occur with so many times, and it turns out that this ratio K over M, that triggers a whole lot of analysis itself. That term, the ratio of K over M, turns out to be very central to a lot of the results. So all I'm saying here is, from now on, let's use this definition. Omega squared is defined as K over M. So this is what I had up here. This is just X force inventory. Here's the same X force inventory with a little rearrangement and with this omega squared. So instead of K over M, I'm just using omega squared. And this is the aha moment. Aha, I know how to solve this. Even if you didn't take differential calculus, which I'm kind of assuming no one has taken differential calculus, although I think some of you might have. But even if you didn't, I would say, well, let's just take a guess. Let's guess at this function right here, right here. Let's guess that this is a solution to this differential equation. And then we would check that. I would say, well, okay. In fact, let me just do, because we're doing okay on time. And not to, well, I can't remember what I did and didn't do in the lecture video, but let's just go through it now. All right, so I would say I need to solve this expression right here. So if I need to solve this expression, I'm going to guess. Here's my guess. I'm going to guess this expression for displacement. So everything is still the same. X means displacement, V means velocity, A means acceleration, F means force, and so on and so forth. All right, so as far as the displacement of this mass is concerned, I'm going to guess this solution. Why do I guess this? Because I know this mass is bouncing back and forth. So this is an informed guess. I know when this block is released, it bounces back and forth, kind of like it bounces back and forth like a pendulum, but it's just a mass on a spring. It bounces back and forth. So that's why cosine catches my eye. I like cosine because cosine behaves like this. Cosine is a bouncy function. You could say, well, why don't you use sine? And I could. So I like the fact that cosine or sine kind of is bouncy. And so I'm going to use that as my guess. And if I say, well, what is the derivative of x with respect to time? The derivative of that function with respect to time is basically xm omega sine omega t plus phi. Check something. Okay. I just wanted to refresh my memory. All right. So that's the negative. So you should know that. You should know how to do that. You know this from your calculus class. All right. So let's take the second derivative. Let's take d squared x dt squared. What's the second derivative? It's going to be negative xm omega squared cosine omega t plus phi. Again, you should know how to do that. So this should be familiar to you. This should be familiar to you. So now I'm going to go back up to this X force inventory. Here's what my X force inventory looks like now. I have d squared x dt squared. So here's the result of d squared x dt squared minus xm omega squared cosine omega t plus phi. And then to that, I need to add, so I need to say plus omega squared times x. There's the omega squared. Here's the x, xm cosine, x is just my displacement function, omega t plus phi. And the question is, does this equal 0? Because if it does equal 0, this in fact is a solution to this second order ordinary homogeneous differential equation. And this does equal 0. So yes, this does equal 0. You can see here that does equal 0. And you know what that means? Good guess. Good guess. It turns out that I can use this as my displacement function. X sub x equals xm cosine omega t plus phi. And then we're off and running, because I know that velocity is dx dt and acceleration is dv dt. But that's enough backstory. I just wanted to go through that and say, using an informed guess that reflects the physical reality of this mass bouncing back and forth. This mass is going to be oscillating back and forth. It's going to go over there and then turn around and come over here and then turn around and go over there. That's an informed guess. So this is what I'm going to take with me for this problem. During the course of solving this, which we kind of did, I'm going to use that omega squared equals k over m. So I'm going to get rid of all of this, since this is just background entertainment. Okay, and let's solve this problem. Number 4, number 5. So when I say, let's look at simple harmonic motion, that is a look at simple harmonic motion. What I just went through was the 25-cent tour representing your $100 premium YouTube lecture video. So make sure that that's another key to success. Watch these lecture videos multiple times. I can't remember. Let me have a timeout. Tangents out of the way. Let's look at simple harmonic motion. According to simple harmonic motion, I'm going to tap in to this. Simple harmonic motion says, well, omega squared equals k over m equals k over m. So you know what that means? That means omega equals the square root of k over m. And this actually has a name. You know omega from the past as angular velocity. Technically now, in this context, in the context of simple harmonic motion, we refer to omega as angular frequency. And this could be confusing. You would kind of be correct to say, like, why do we have to use a different name? And it's because we're talking about simple harmonic motion. Angular frequency, not angular velocity, angular frequency. And you know, one way to remember that, this helps me. What are the units for omega? Omega is radians per second. Anytime you have something per second, so anytime you have like just whatever, x equals something per second. Anytime you have something per second, this can be referred to as a frequency. A frequency is something per second. So in the case of omega, what do we have per second? We have a certain amount of angle. So this is basically angle per second. Angle per second is angular frequency. Just like we had f equals cycles per second. Cycles per second is a frequency. You could say the rate of people arriving to your Thanksgiving celebration. You could say there are 3 people arriving to my house every hour. This would be your frequency. Your frequency would be 3 people per hour. So this would be people frequency. This is angular frequency. All right. So now, having said all of that, that's why the term angular frequency is used. And I think I have to restart something. Do I? Okay. So the good news is birth of a radian reminds us that, well, omega is also equal to 2 pi over t. This is brought to you by birth of a radian and let me just go through this. I'm going through this not because I'm looking for ways to fill time. We don't have a lot of time, but I want to basically say that birth of a radian started with theta is defined as S over R. That's the definition for radian measure. And from there, we said S equals R theta. Then if you divide that by time, if I divide the left side by time, I have V equals R omega. And if I remember what velocity is, well, for something moving in a circle, velocity is distance, 2 pi R divided by time. So that's what happens to velocity on the left side of the equal sign. Here's the right side of my equal sign. So this is how you get omega equals 2 pi over t. And I remember that period and frequency are reciprocals of each other. Anyway, this birth of a radian, trip down memory lane, is what does produce this expression for omega as well. So we have two equivalent expressions for omega. This is omega in the context of a spring mass system. This is omega, generally speaking. So this is the general expression for omega. This is the specific expression for omega for a spring mass system. And from here, I can get mass. I can get M2, and I better worry about subscripts because it's M2. M2 is the mass bouncing back and forth. So I'm just going to add that as a subscript. Otherwise, that's risky. Okay, so this is mass 2, M2. And then let's solve for mass 2. And then keep going on our merry way to do, we're doing momentum, and then we're going to do kinematics. This will be a two-dimensional projectile. So it's a good problem. All right, so number 6 is saying solve for M2. So if I square both sides, if I look at number 5, here's my new number 5. My new number 5, if I square both sides, I have K over M2 equals 4 pi squared over T squared. And I got to get M2 all by itself. M2 equals KT squared all over 4 pi squared. Right? Right. So let's get a value for M2 and let's put it in calculator memory location A. We can do that right now. Lots of dimensional analysis to do, but I will sidestep that for now. Okay, so I have a value for M2, store alpha A. Let me do it again. Stiffness constant. All right, I'm getting the same answer twice. That's comforting. All right, so let's go back to we're going to revisit number 3. Here's my updated version of statement 3. I have the velocity of block 1 after the collision is going to equal 0.220 kilograms minus mass 2, which is sitting there in calculator memory location A, all over 0.220 kilograms plus mass 2 times the mass 1 incoming velocity. So again, I'm just keying right here. V1 initial, the velocity of block 1 as it was colliding with block 2 was 7.55 meters per second. 7.55 meters per second. So let's put that in calculator memory location B. And what's the negative? Negative, I think the negative makes sense. I'm going to redo it. All right, same answer twice. And that the negative makes sense. I actually, with my numbers produce negative 2.67 and some change, negative 2.67 meters per second, which does make sense because M1, after the collision, M1 goes flying off the tabletop. So now it's just two-dimensional kinematics. This is something we covered literally the first week in class. In fact, there was a whole lab dedicated to two-dimensional projectile number 8. Here goes. X initial, X final, Vx initial, Vx final, A sub X, and T. Two-dimensional kinematics means I have an X dimension and a Y dimension. Y initial, Y final, Vy initial, Vy final, A sub Y, and T. And what do I know? I know X initial is 0. So here's X initial equals 0. Here's X final right here. This is X final is my dollar sign. So dollar sign for X final. Here's Vx initial. Vx initial is going to be whatever's sitting there in calculator memory location B. Got it? Vx final, there's no acceleration as this is traveling through open space, ace, because there's no x acceleration. Time is, I don't know. As far as y is concerned, starts off at an initial height of h, which for me, h is, do I know what h is? Yeah, 6.5. This is 6.5 meters. This is 0. So this would be y final equals 0. This would be y initial equals h equals, for me, 6.5. Vy initial 0. It's a perfectly horizontal launch. Vy final is, I don't know. A sub y negative 9.8 meters per second squared T. And we remember, I remember, hopefully you remember, the hope is everyone remembers that for a two-dimensional projectile, we get flight time from the y data table. And then we can go back and use that flight time for the x data table to find out the dollar sign. So step number 9, let's find the flight time from the y data table. Okay, so that would be, I'm going to guess this. This is, it's another guess and check situation, but we have some practice here. But I'm going to guess y final equals y initial plus vy initial t plus 1/2 a sub y t squared. Again, and I included the big 5 right here. You get to you can only use these if you know for sure the acceleration is constant. And we do know the acceleration is constant. It's just the acceleration here is just equal to negative g. And that's a constant. There's no variables there. All right. So let's get time of flight. 0 equals 6.5 low-hanging fruit minus 4.9 t squared. So for me, here's my time of flight. T equals the square root of 6.5 meters all over 4.9 meters per second squared. So I can see the dimensions is going to work. I will get seconds. Whatever this works out to be, I'm going to put this in calculator memory location C. That is my time of flight. .1.15 and some change. 1.151 seconds and some change, and store alpha C. And to conclude, look at X. Let's look at X data. We've done this too many times to remember. The same approach for a 2D projectile. So if I look at the X data, X final, which is my dollar sign, equals X initial plus VX initial times time plus 1/2 A sub X T squared, which is how I get X final equals X initial. That was set to 0. VX initial is sitting there in calculator memory location B. Time is sitting here in calculator memory location C. So when I just do those two calculator memory locations, calc memory B times calc memory C, I get alpha B times alpha C. Negative 3.08 and some change, negative 3.08077 meters. And they just want the magnitude. So ignore negative sign. So what a great problem. We have momentum. We have simple harmonic motion. We have kinematics analysis method. All right. And our first brush with simple harmonic motion. Let me get the next quiz ready. I think the next quiz is already there. Let me clear the clutter. Let me check. Quiz 2 should be problem 33. Let me just sanity check that for myself. Chapter 15, quiz 2. Chapter 15, quiz 2 is hopefully problem 33. Okay. All right. Similar kind of problem, similar-ish, different enough to be beneficial. All right. Now here, let's see. It's yet another spring mass system. So I have a spring mass system, which is an example of simple harmonic motion. And it turns out a lot of things behave this way, even complicated stuff, even things that don't on the surface look at all like a simple spring mass system behave like this. Here we have a bullet. You're firing a bullet at this mass. A block of mass M equals 5.2 kilograms is at rest on a frictionless table. It's attached to a spring with a known spring constant. You shoot this little bullet, it embeds itself in the block. So that's perfectly inelastic collision. We need to figure out the speed of the block immediately after the collision. So let's go with this. Number one, it's a collision. So once again, this is my first thought. It's a collision. Not only is it a collision, it's a perfectly inelastic collision. Perfectly inelastic collision. So this is my starting out position. And if I keep going down this path, hopefully I'm going to find out the speed of the block immediately after the collision. And for part B, the amplitude of the resulting bouncing back and forth. All right, so momentum is always conserved unless there's an external force, which there's no mention of an external force here. There are forces when this bullet crashes into the block, there are forces, but they're opposite and equal. So they just cancel each other out. Conservation of momentum says that, which means the following: whatever the initial momentum is must be the same as the final momentum. And here's my initial momentum. I'm gonna call this M1 just because I don't like little m, big M. It's just cumbersome. So I'm gonna call this, the bullet will be M1 M1, and the block will be M2. Just, it's easier instead of me trying to always write little m and big M. The bullet is M1, the block is M2. So before the collision, I have mass of the bullet times the velocity of the bullet. And that's my momentum before the collision. What is my momentum after the collision? Well, M1 and M2 become a single object. The bullet embeds itself in the block. And then this would be V final. So let's solve for V final. V final is going to equal M1 V1 all over M1 plus M2. So with numbers, M1 is that little teeny tiny bullet, which is 8.9 grams. So it's going to be 0.0089 kilograms times the velocity. This is a bullet, so it's going fast, 730 meters per second. That's my numerator. Here's my denominator. M1 plus M2. Do I know both of those? I do. M1 is the bullet, so that's 0.0089 kilograms because 8.9 grams is that many grams times, or I should say plus kilograms, plus the mass of the block, which is 5.2 kilograms. So here's the answer to part A. The velocity of the block immediately after the collision, 0.0089 times 730. Okay, 1.24 and some change. So we're done with half the problem. 1.247 meters per second. This is calculator. Let's put that. Calculator memory location A, store alpha A. Part B says, what's the amplitude of the resulting simple harmonic motion? Okay. So when this bullet crashes into the block is going to go bouncing back and forth. The block with the bullet embedded in it is going to go over here for a while, and then it's going to bounce back and forth according to simple harmonic motion. So it's going to oscillate back and forth because of the kick it got from that bullet. So it's bouncing back and forth according to simple harmonic motion. So number 4, let's look at simple harmonic motion. All right, so I'm going to start with this. Ready, set, go. Here's a displacement function. Okay, so I talked about this previously. This was my guess, and it turns out this was an informed guess, and it turns out this guess was correct. So this is what we're using for displacement. You know what this is saying? This is saying the location of object at some time t, That's what this is referring to. What is this? This is a special term. This is called displacement amplitude. Anytime you use the word amplitude, it means max value of. Displacement amplitude. This is the maximum displacement with respect to equilibrium. So this box is bouncing back and forth. If this box is bouncing back and forth, and if I graphed it, here's the box bouncing back and forth. It's going back and forth because it's attached to a spring. It's bouncing back and forth. This is displacement magnitude. So this peak point right here, whatever this distance is with respect to the equilibrium right there, this is x sub m. And you could say, if you wanted to, you could say, hey, Chris, isn't this the same value right here? And the answer is yes. This is also x subscript m. So that's the displacement magnitude. This is just for the sake of repetition. This is the angular frequency because the units are radians per second, which is a frequency. Angular frequency, this is T stands for time. And then this is phase shift. So phase shift basically keeps track of if the object has a head start or if it's lagging behind. So for example, if you're racing in a 100-meter dash and you walk 10 steps in front of the starting line, giving yourself a head start, your phase shift would be 10 steps. If on the other hand, you walk 10 steps behind the starting line, you would be putting yourself at a distinct disadvantage. But forget the advantage or disadvantage. But if you step 5 steps behind the starting line in a 100-meter dash, your phase shift would be 5 steps going in that direction. So this phase shift is used to figure out, well, where are we? Are we starting right at the starting line, or are we starting up maybe in front of the starting line, or are we starting behind the starting line? All right, so that is our displacement function. I know I'm saying a lot about that, but if you don't have, if we don't cover it to this detail, you basically just become an equation operator. You're just plugging numbers into an equation and crossing your fingers that the right answer pops out, which to me that's just too darn stressful. That's just like playing Russian roulette. So now I'm going to take the first derivative of this function. Ready, set. As soon as I get, all right, so number 6, velocity is still dx dt. So let's take the first derivative of this displacement function, x sub m cosine omega t plus phi. And everyone here needs to know how to take that derivative. That derivative is going to equal negative omega x sub m sine of omega t plus phi. All right. So great. That's the velocity. Now, here's a unit circle question. Here's a unit circle. Well, maybe not so much a question, just a recap. So here's the unit circle. I've referred to this a lot. Turns out this is like fundamentally important in so many ways. All right, so here's the unit circle. This is the x-axis. This is the x-axis, but in terms of the unit circle, we're going to refer to this as the cosine axis. That's my cosine axis. This is the y-axis, but in the unit circle world, we refer to this as the sine axis. If I have some angle, so let's just say I'm sitting right here at this location. I'm making a certain angle theta. So this is theta. Whatever this projected value is right here from that object, that's from you down to the cosine axis. Whatever this value is right here, this is the cosine of theta. If I project this leftward to the y-axis, like this, whatever that value is right here, we call that sine theta. This unit circle means this radius is 1. Okay. So the greatest value cosine can ever attain is 1. Cosine can have a maximum value of 1. It can have a minimum value of -1 and everything in between. So this is -1. This is +1 for cosine. For sine, sine can be as great as +1. And sine can be as negative as -1 and everything in between. So I'm doing this for a reason, even though you might know this very thoroughly, but this right here, the maximum value the sine function can ever attain is 1. So we have a term called velocity amplitude. So it's the same naming convention. velocity amplitude is the maximum value of velocity. So the good thing about this expression right here, this is telling me my velocity at any moment in time, because remember what that is. This equals velocity as a function of time. So again, that's the good news, is at any moment in time, I can tell you what the velocity is, but I know whatever time, whatever the case is, the maximum value of velocity is right here. This is velocity amplitude. This is the maximum possible value of velocity. So we've talked about displacement amplitude. Now we're talking about velocity amplitude, and we'll have the exact same conversation for acceleration amplitude and force amplitude. But velocity amplitude equals V subscript M for like max value equals omega X sub M. That is the velocity. That's the maximum velocity. So part B of our question says, what is the amplitude of the resulting simple harmonic motion? So here it's the good news, bad news situation. We don't care about velocity amplitude. That's the bad news, but we will, I think, in the next problem. So I read this wrong. It says, it didn't say what is the velocity amplitude. It's saying what is the amplitude of the resulting simple harmonic motion. So now as I'm sitting here reading this carefully this time, this is talking about X sub M, not V sub M. It's not talking about velocity amplitude. It's talking about X sub M. So, well, actually, maybe this isn't wasted time. So how do we get that? All right. I guess I needed that after all. So I'm going to retract my apology. All right. So, well, VM equals whatever I have here in calculator memory location A, because after the bullet embeds itself in the block, immediately it will start to slow down. The spring acts like a brake. The bullet smashes into the block. The slowing down happens immediately, because if I try to compress the spring's going to fight back. So whatever this value is for you, this is the high water mark. Your velocity will never be greater than what we got from part A, because as soon as that collision occurs, the spring is going to start slowing things down. So I guess I do need all of this. Number 9. All right, so velocity amplitude equals calculator memory location A, and through all of this step 5 and 6 in my unit circle diagram says that also equals omega X sub M. So number 10, here's the displacement magnitude. X sub M equals calculator memory location A all over omega. And now what do we do about omega? Don't know omega. So number 11, remember, omega for a simple harmonic oscillator equals the square root of K over M. Well, all right. Now here we need to be careful. I know what K is. K is given, and the spring stiffness constant is never going to change. So what do I use for M? Is this is this M1? Is this M2? Is it M1 plus M2? I think this is M1 plus M2, because we're being asked to figure out what's going on after the collision. All right, so that's my thought process, because there are some choices here. Omega equals the square root of the spring stiffness constant, 5380 newtons per meter. That's my numerator. My denominator, because again, we need to study what's happening after the embedding occurs, is going to be those two So let's see, for me, M1, it would be 5.2 kilograms plus 0.0089 kilograms. And that's how I'm going to get my omega. And I'll put that in memory location B. $53.80. All right. B. So you know what that means. Number 13. Let's go back to number 10. So here's the new number 10. This object is going to bounce back and forth with this amplitude. Okay, 0.038. There it is. Another momentum and more momentum in simple harmonic motion, but this gave me a chance to rant a little bit about velocity, amplitude, and the unit circle, all very recyclable topics. So that is, it's 2:02. So I will see you at 2:09. And we're back. Chapter 15, quiz 3 is next. Phase angle. So this is a problem just to teach us, provide insight to what a phase angle is. Okay. Let me do this. Let me go to Desmos. Desmos. All right, look at this. Here's a cosine function. Y equals cosine of x. Okay. Garden variety cosine function. What if I repeat this down here? What if I say y equals cosine of x plus pi over 6, which is 30 degrees. So let me fix that there. All right, so now here's my original cosine function. This red function is my unshifted starting right at the starting line cosine function. Here's what happens when I give myself a phase shift. This phase shift of positive pi over 6 actually puts me behind the starting line. So this blue function is the same as the red function in every way, except it's starting behind by pi over 6 radians, which is 30 degrees. What if, on the other hand, I have another one, y equals cosine of x plus pi over 2, 90 degrees. And instead of plus, maybe I'll say negative, minus. All right, so look at this. Look at this green function. This green function is just like the red function, but it's phase shifted pi over 2 radians ahead of the starting line. So there you have, it's good to see this side by side. Here's my unshifted cosine function. Here's a cosine function shifted backwards 30 degrees. Here's a phase shifted cosine function shifted forward by 90 degrees. So those are all the same. In fact, what if I did this? What if I get rid of that? What if I said, what is cosine of pi over 2? Well, look at, let me do this. What does this blue function look like? This blue function is a sine function. And so you know what you can say. Do you know that a sine function is nothing more than a cosine function shifted forward by 90 degrees? Here's my cosine function, red. Here's my phase shifted cosine function, which is the same as the sine function. So anyway, that's what phase shift is referring to. For our problem here, we need to, if the phase angle is pi over 4, which is 45 degrees. So we have a phase shift of 45 degrees. So you know what, let's just get a visual on that one more time, just to, I don't know if it's forward or backwards. So, but I do know it's pi over 4. There it is. So notice that here's my unshifted cosine function. This blue function is behaving exactly the same way, but notice where I'm starting. I'm starting at root 2 over 2. I'm starting at some value that's less than 1, whereas for an unshifted cosine function, check this out. My cosine function is starting off at its peak value. There's no shifting going on. I'm starting right at the starting line, whereas this shifted function here, I'm starting at some value, not quite at the peak. Okay, so wanted to talk about that again. Here's what we need to do. With this phase shift in mind, what's the ratio of kinetic energy to potential energy at some time? So here goes number 1. This is the dollar sign. What is the ratio of kinetic energy to potential energy at t equals 0? That's the dollar sign, this ratio. So number 2, well, kinetic energy is 1/2 mv squared. And potential energy for a spring is 1/2 kx squared. So let's do some low-hanging fruit right now. So the ratio of kinetic energy to potential energy is 1/2 mv squared all over 1/2 k x squared equals mv squared over k x squared. Okay, so let's keep going with this. Once again, oh, they actually gave it to you. So they said, in case you forgot, this is our displacement function. So at any moment in time, my displacement function is x sub m cosine omega t plus the phase shift. My velocity, v equals dx dt equals minus omega x sub m sine omega t plus phi. All right, so let's go to this is step number 4, step number 5, step number 6. So this ratio is equal to mv squared. So here's mass. Here's velocity squared. I need to take this entire function, negative omega x sub m sine of omega t plus phi. I'm going to take this whole function and square it. There's mv squared. That's my numerator. Here's my denominator, k x squared. And here's x. This is x, xm cosine omega t plus phi. Square that. So you know what this ratio becomes. K over u is now equal. Well, let's see here. Some low-hanging fruit. T equals 0. So this equals 0. This equals 0. Phi is pi over 4. For me, it is. That's what's given. So, you know, with those givens stated in the problem statement, I have, and I'm squaring things now. This is going to be my numerator is going to be mass times omega squared xm squared sine squared of pi over 4. My denominator is going to be k times that argument squared, xm squared, cosine squared of pi over 4. Okay. Low hanging fruit. The xm's cancel. All right, so here's the answer. This is going to equal mass over K times omega squared. Because let's talk about what's the sign of pi over 4? You either know this from your unit circle, and if you don't know that from your unit circle, you could just say sine of pi over 4, which is 45 degrees, or root 2 over 2. Sine of pi over 4, according to my calculator, is root 2 over 2. And you know what? Cosine of pi over 4 also equals root 2 over 2. So more low-hanging fruit. These cancel. Okay, so this really is the answer, but wait, there's more. This really is the ratio of kinetic energy to potential energy. Number 8, let's use omega squared is defined as K over M. So here's what I have. The ratio of kinetic energy to potential energy is going to be M over K times omega squared, which is K over M equals 1. So kind of anticlimactic, but it's a good chance to talk about phase shift more than anything. And it reminds us there's still such thing as kinetic energy and potential energy in simple harmonic motion. So that's a good reminder. That didn't take much time. On to quiz 4. Let me come back. Quiz 4 should be 34.
All right, quick question.
Mm-hmm.
So if the phase shift is pi over 3,
Mm-hmm.
so sine would be then it's square root of 3 over 2, and then cosine's a half.
Yeah.
But does that still equal out?
No, they don't cancel. You have to drag those along.
Yeah. So that would
mine
be
was anticlimactic. You probably have a more interesting situation.
okay.
Right.
Just
That's good.
checking.
You're right. Time check, 221. Okay, so if I did my part, chapter 15, quiz 4 should be homework problem 34. Another one of these problems. Looking kind of familiar, except now this is going to be a little bit more. Well, we'll find out. Once again, we have a collision, except now block 2 is bouncing back and forth. Block 2 is oscillating. So block 2 is not just sitting there at rest. Block 2 is undergoing simple harmonic motion. And in fact, we know the period. This is the period T for M2. So for sure, it's bouncing back and forth according to simple harmonic motion. We know the position. So here, you know what? For M2, they gave us. They're saying, hey, Here's your position function, your displacement function, x equals 1.90 centimeters times the cosine of omega t plus pi over 2. Okay. And I'm just going to, right underneath it, I'm going to write down the generic expression for displacement of a object undergoing simple harmonic motion is going to be xm times cosine of omega t plus phi. So from these equations, we can see that xm equals 1.9 centimeters and my phase shift is 90 degrees or pi over 2 radians. So, all right, that's true for the block that's bouncing back and forth. Block 1 impacts block 2 with a velocity directed along the spring's path, and they stick together. All right, so they stick together. They stick together. The collision occurs at 7 milliseconds and they stick together. What is the amplitude of the simple harmonic motion? So this is what we're looking for. We're looking for xm equals $. Xm for the combined M1 plus M2. This is what the problem is saying. Block 1 and block 2 stick together. What is their resulting amplitude as they continue to bounce back and forth? So step number 2, because I'm thinking, remember, conservation of momentum for a perfectly inelastic collision says delta P equals 0, which means my initial momentum equals my final momentum. Okay, so is this a stationary target? So, so because you know what I'm thinking, well, all right, here's my initial momentum. My initial momentum is mass 1, velocity of 1 initial, plus mass 2, velocity of 2 initial. And whatever that is, they stick together. So it's M1 plus M2 times whatever final velocity those combined blocks have. So the big question right now is, what is the velocity of block 2 upon the collision and the collision happens at t equals 7.00 milliseconds. I need to find out the velocity of mass 2. Okay, at 7 milliseconds. Number 4. Well, here's my displacement function. X is equal, my displacement function, 1.90 centimeters cosine omega t plus pi over 2. Let's take the derivative of that to get the velocity function. The derivative, if I take dx dt, equals negative 1.90 centimeters times that omega times sine of omega t. Well, actually, t is 0.007 seconds. Omega times t. Here's t, 0.007 seconds plus pi over 2. That's my phase shift. It's starting behind the starting line. Number 6, what's omega? Omega equals, I don't know, but I do know that omega is k over m period. So I know omega, can I use this? Omega equals 2 pi over t, and they're giving me the, okay, yes, and they're giving my period. So you know what, for block 2, omega equals, because block 2 is the only block moving with simple harmonic motion, it's going to be 2 pi all over the period, which is given as 28 milliseconds, 0.028 seconds. Let's just stick this here in calculator memory location A. That's my omega. 2 times pi divided by 0.028. Store alpha A. So let me just do that again. What is 2 times pi divided by 0.028? All right, I'm getting the same answer twice. So now we can figure out the velocity. Once again, at t equals 7 milliseconds, I can say my velocity at 7 milliseconds equals negative 1.90 centimeters times omega. And omega is going to be calculator memory location A times sine of omega times t. Here's omega, calculator memory location A times 0.007 seconds plus pi over 2. Plus pi over 2. Let's crunch numbers. When I do this, well, let me withhold V at 0.007 seconds. So let's see. You know what I get? I get 0. Make sure your degree is, if you do this, you guys, make sure you're in degree mode. I'm sorry, make sure you're in radian mode. So because this is radians. When I crunch these numbers and I have my calculator sitting in radian mode, I don't really have to do that, but well, because I can see for me, this value came out to be 3.1415. Basically, this value came out to be pi. And I know the sine of pi equals 0 thanks to the unit circle. I don't even care what this is, because if my sine is spitting out a value of 0, then it doesn't matter what this term is. I have a velocity of 0 meters per second. So here's the big takeaway. Number 10. At t equals 0.007 seconds, m2 velocity equals 0. It's a stationary target. So that's good to know. So because it's a stationary target, I'm going to go back to number 2. So here's my new number 2. My new number 2 is saying the following. Low-hanging fruit, this equals 0. So it's momentarily stopped. At the moment of collision, block 2 has a velocity of 0 just at that moment. If it's any time earlier or later, it doesn't have a 0 velocity, but at that moment, it does have a 0 velocity. So I'm going to find out what is the amplitude. I'm going to find out the velocity of the combined blocks because they stick together. So ready. My new number 2 says mass 1 times the velocity of 1 before the collision equals, they stick together, mass 1 plus mass 2 times the final velocity. So that means the final velocity after the collision is equal to mass 1 V1 initial all over mass 1 plus mass 2. And we have all these numbers, don't we? Mass 1 is 5.6. So I need to take 5.6 kilograms, multiply it by the velocity of mass 1, the incoming velocity, which is 6.9 meters per second. That's the incoming velocity before the collision of mass 1, because mass 2 is just a sitting target, all over 5.6 plus mass 2, which is 2.8 kilograms. So I'm getting a velocity after that impact. My velocity is okay, 4.6. In fact, it's a positive 4.6. So the and that's kind of to be expected. Positive 4.6 meters per second for the combined for M1 plus M2. Okay, so knowing that that's the velocity, let's see here. We got to think about this. What is the amplitude of the simple harmonic motion after the collision? All right, so this is interesting. Because the mass 2 is not at equilibrium. So let's see, thought process. We need to think carefully about this. So this is number 12. Number 13. Careful. Careful. Mass 2 is not at equilibrium. It's at its extreme elongation. Mass 2 is actually at its longest stretch possible. All right, so what is the amplitude? Well, here's the amplitude. X sub m. We're looking for X sub m. I'm going to do energy analysis. I can't think of an alternative, because this is what I'm thinking. I have here's block 1. Block 1 at the moment of impact, right here. Here's block 1. Block 1. There's block 1 making contact with block 2. I'm going to call this energy state A. And then block 1 and block 2 are going to keep going to the right and slow down to a stop. So here's block 1 and block 2 over here. Once they've come to a stop, there's block 2. And here's block 1 stuck to it. And I'm going to refer to this as energy state B. Okay. Energy state B. All right. What is the amplitude? So let's do energy analysis. There's no friction going on. So number 14, whatever energy I have at A plus non-conservative work that adds energy or steals energy equals my energy at B. Number 15 becomes number 15. Well, at energy state A, I could have some kinetic energy. I could have some potential energy. There's no non-conservative work, so that equals 0. At B, I could have some kinetic energy, and I could have some elastic potential energy. Okay. Any low-hanging fruit here? Yes, there is. At B, at energy state B is the point of maximum compression. So this is going to equal 0. And I'll say at B, at energy state B, M1 plus M2 slow to a stop. That's what I'm calling energy state B, slow to a stop. Okay, so any other low-hanging fruit? No, because I have some elastic potential energy at A and I have some elastic potential energy at B. So let's keep going with this. Number 16 over here, I guess. All right, number 16 at A. Here is my kinetic energy, 1/2 mv a squared. This is my kinetic energy. Here's my here is my potential energy, 1/2 k x a squared. So that's what's happening at energy state A. Here's what's happening at energy state B. There's no kinetic energy, but there is some potential energy, 1/2 k xb squared. So this is kind of teeny tiny to look at, but right here, block 1 and block 2 are stretching the spring, are compressing the spring. So the spring compresses by xb. Okay, so that's kind of cumbersome. Let me just say here, here, spring is compressed by xb meters, and that's our dollar sign. This is the dollar sign right here. This point of maximum compression. Okay, this is dollar sign. Okay, so step 17. Ready. 1/2 times mass. So this will be M1 plus M2. What is the velocity at A? At A, that is the velocity upon impact. And we figured that out. Step 3. Didn't we figure that out somewhere? Yeah. That's right here. 4.6 times 4.6 meters per second. So let's sanity check this. This came from momentum, perfectly inelastic collision. Right after the collision, M1 and M2 stuck together and they had a velocity at that moment in time of 4.6 meters per second. That's not a maximum velocity because you know what? Things are actually going to speed up. Because not only do we have the incoming velocity of mass 1, but mass 2 is now going to convert some of its elastic potential energy into kinetic energy. So that is, whatever that is, that's the velocity at upon impact at energy state A plus 1/2 k. I guess I'm mixing variables and numbers. What's XA? You know what that is? XA is 0.019 meters squared. Okay, so a note about that here as well. At impact, M2 is at maximum stretch, maximum elongation. We showed that. Okay. So maximum elongation, because at the moment of impact, its velocity was 0. So we showed that here. When the velocity, so just look at a mass bouncing back and forth. If this is a mass, let me just draw it like this. Okay. If this is a mass bouncing back and forth, it's bouncing back and forth, back and forth. at this extreme point here, zero velocity. At this extreme point here, zero velocity. At the midpoint, maximum velocity. So as this is bouncing back and forth, that's actually a pretty good little artifact. Oh, there it goes. But as this is bouncing back and forth, when it's way over here, it has zero velocity. When it's way over here, it has zero velocity. So I can just label that. This is no velocity. This is no velocity. This is maximum velocity right here. This is max stretch, or I guess you could say in this case, this would be max compression. Max compression. And this would be max elongation. Okay, so that's what's going on. So that's why I'm saying, I'm going all the way back to step one. Step one is saying, hey, the position as a function of time is given right here. So what is the maximum position mass 2 can have? The answer is 1.9 centimeters with my numbers. 1.9 centimeters is the amplitude. This is x sub m. So that's where this number comes from. This number is the amount of spring stretch at that particular moment when M1 collides with M2. That's the left side. The right side is equal to 1/2 kx squared. Let me move this. Okay. The right side is 1/2 k xb squared, and there's your dollar sign. So some low-hanging fruit. We can cancel out the 1/2s. 1/2 cancels there, cancels here, cancels there. You know everything else. Solve for xb. That will be the maximum compression, and that corresponds to amplitude. Number 18. Solve for x subscript b. Let me do it too. Oh, and I forgot the squared. So typo alert. Typo, this should have a squared. Oh no, we don't know what K is, do we? We don't know what K is. That's the bad news. So the good news is I think it's going to be pretty easy to figure out, but we don't know it. I thought it was given. All right, back to it. Number 19. What's K? Did we figure out K? I mean, we're going to be able to. All right, so what's K? I'm going to tap into omega is defined, well, omega squared is defined as K over M. So you know what that means. K is going to equal M omega squared. But now here's the question. What do we use for M? I'm going back up here. Before the collision, block 2 was bouncing back and forth with that period. 0.28 seconds. In fact, I have omega right here. Right, so you know what? I'm just gonna. There's my omega. Is it still sitting there in memory location A? 2 pi divided by 0.028. Okay, that is. So I already have omega, so I'm gonna repurpose it. But the K value corresponds to M2. So this is going to be M2 times omega squared. And my M2 is 2.8 kilograms times omega squared, or alpha A squared, equals 2.8 times alpha A equals some big number. I'll put that in calculator memory location C. Okay. Okay, and let me see. Let me just double check. Is it M2? Yeah, because it's mass 2 that has an oscillation period of 28 milliseconds. So 2 times pi divided by 28 milliseconds. Yep, that's omega. I square that times 2.8. All right, that's the same answer twice. So now we can solve for. Go back to 17. So solve for XB in number 17. All right. After the collision, M1 and M2 for me are going to be bouncing back and forth with this amplitude. So we use momentum, simple harmonic motion, and energy analysis. So all of these problems are pretty darned rich in terms of what we have to scrape together. What time is it? 2:50. Let me do a check on this problem. That's pretty involved. Well, we'll start the next problem and take a break before we finish the whole thing, but finish this one up if you still need another moment. The next quiz 5, is problem 35. Let me get that ready.
Professor, did you watch the game on Saturday?
Yeah, I was there.
Oh, you were there? Oh,
And I'm
awesome.
I'm going to the championship game in Indianapolis this Saturday with the whole family.
I gotta be honest, I was not expecting that to
Oh.
happen. But
It was shocking.
were you on the field like after the game ended or no?
No, I let the younger people wreak mayhem on that. It was crazy though. I mean, it was the most exciting game I've ever been, literally since 1979. I was at the Michigan Indiana game, and that was like a last minute victory. This was bigger. This was a bigger victory, I think. So quiz 5. All right. Chapter 15, quiz 5. I think I have this set up correctly. Okay. Chapter 15, quiz 5. One of these multi-part. I always like these types of prompts because it's not tricky. It's just saying, hey, go ahead and find out all the basics. It's not like a real super brain teaser. It's just saying, hey, figure out the basic properties. Okay. a particle undergoes simple harmonic motion with a certain amplitude and a certain maximum acceleration and an unknown phase angle. What's the period of motion? So just for the sake of a visual, I'm going to do this. I'm going to do like a bead on a wire. So here's a wire. This is a wire. And along this wire, we have a big red bead. All right, an 88 kilogram particle undergoes simple harmonic motion. Is there anything? They don't say anything about a spring. So you know what? It might not be making, a spring might not be involved here. There are many other things. There are many other kind of forces. The only thing we care about is whatever the force is that's acting on this particle. It has to be a restorative force that's linearly related to displacement. This could be from a spring. A spring could do that, or it could be some kind of combination, a combo of maybe, for example, electric fields or some other, maybe a mechanical. Maybe you have an actuator. An actuator is basically a device that pushes and pulls. Maybe you have an actuator that's somehow behaving according to F equals minus KX, because it's not mentioning anything about a spring. So there's my visual. Let's just do number one, 88 gram particle undergoing SHM. All right, so here's, this is XM equals 0.0096 meters. This is mass. Mass equals 0.088 kilograms. We have, for the first time, we have maximum acceleration. So this number right here, this is acceleration amplitude. Okay. And I don't know what the phase constant is. So part A, what's the period of motion? So T, for part A, they're saying find out how much time it takes to complete one cycle. So that's the dollar sign. Okay. Well, let's see. I don't know what to do. So I'm going to bark up this tree. I know that the velocity magnitude, I did the heavy lifting on that. And I said, well, the velocity magnitude is omega times x sub m. Okay. So now I'm just going to do the same little sidebar for acceleration. Did you know that acceleration is defined as dv dt? So I'm going to take the time derivative of the velocity function. This was my velocity function. My velocity function was minus omega x sub m sine omega t plus phi. This is, one more time, let me say it, this is velocity as a function of time. This argument. Velocity as a function of time, and that was referenced back here somewhere. Right here. So this was proof of that, or the development of that. So I'm taking this velocity function right here, and if I take the derivative of it, that's going to tell me what the acceleration is. So if I take the derivative of that, number 4, the acceleration is going to, which is a function of time. So that's how I, argument T means function of time, equals minus omega squared x sub m cosine omega t plus phi. So that's me taking the first derivative of my velocity function. As mentioned, at most, this can spit out a value of 1. So this is my acceleration amplitude. This is the maximum possible value that acceleration can attain. Number 5. A sub m acceleration magnitude equals omega squared x sub m. We don't include the negative. We just want this magnitude. All right. So number 6. Aha. The maximum acceleration magnitude for me is 9.7 e minus 3 meters per second squared. That's the maximum acceleration, which means that is what equals omega squared times x sub m. So let's
I'm sorry, isn't it 9.7 e positive 3?
Yeah, you're right. Thank you. 9.7 e positive 3. Good catch. Okay. So let's isolate omega. So omega squared. So that means omega squared equals 9,700 meters per second squared all over x sub m. What's x sub m? That's given to us. X sub m is 0.0096 meters. That's your omega squared. And you can remember, so you're going to take that and you're going to say, well, if that's omega squared, I know that omega also equals 2 pi over t. So then just solve for t. Solve for t, and that will be the answer to part A. Because I know I'm going to get omega squared thanks to maximum acceleration. All right, and then I know what to do with that. Okay. Seconds. This is the answer to part A. I'm going to keep this. Okay. 1 down, 4 to go. And time check, 3 o'clock. Maybe let's do part B. What's the maximum speed? Actually, this could go pretty fast. We'll see. We'll see how my endurance holds out. What is the maximum speed? So for part B is saying the maximum speed is the $sign. The velocity amplitude is the $sign. And I know through previous conversation, the velocity amplitude, which is the maximum velocity, is equal to omega x sub m. So I'm good to go there because I know what omega is, and I know what x sub m is. Okay, so let's just do that. 9,700, should have stored that. Point. Oh. Okay. Done with part B. 9.6498 meters per second. That once again is the velocity amplitude. That's the answer to part B. I'm going to store that just because you never know. Store alpha B. 2 down, 3 to go. Maybe the rest of this is that easy. Part C says, what is the magnitude of the force on the particle when the particle is at its maximum displacement? Well, that's a good question. So here's part C. I'm going to go back to my visual. All right, so this particle is going to go oscillating over here. It's going to go to the extreme left, slow down, stop, and then stop, and then go over here to the extreme right. All right, so here's the simple harmonic motion. It's basically doing this oscillating back and forth between those two extreme endpoints. So here, this is V equals V max. That's my maximum velocity. This is V equals 0. This is V equals 0. This is X equal 0. This is X equals the max value. And this is X equal, I guess you could say, negative max value. What about acceleration? What's going on with acceleration? Here's what I have for acceleration. Here's position. Position equals xm cosine omega t plus phi. Here's velocity. Velocity equals negative xm times omega sine of omega t plus phi. Here is acceleration, negative xm omega squared cosine. So those are my three functions stacked. You know what I'm going to do? I'm going to just bounce into Desmos, and I'm going to call this one. So I'm going to just say this is going to equal 1. So I'm going to make my life really easy. When I get into Desmos, this is what I'm going to do. I'm going to set xm equals to 1. I'm going to set omega equals to 1, and I'm going to set phi equal to 0, just to make my life easier. So if I go into Desmos, I just want to see what these curves look like stacked right on top of each other, kind of like I did before. So here's Desmos. Here's my displacement function. All right, so let me make sure I'm sharing. Here's my displacement function. Y equals cosine of x. Fine. Here's my velocity function. V equals negative, maybe -2. I'll just give it some amplitude of times sine of x. That's my velocity function. Here's my acceleration function. A equals negative some value, -3 times cosine of x. Okay. All right, so I got to figure out, where do I have a maximum acceleration? Right here. Here's a maximum acceleration. What's going on when I have this maximum acceleration? Let me just add an x equals pi. So let's see, x equals pi. Right here, this blue line. So this green curve is my acceleration. That's when I have a maximum value. It occurs when velocity equals 0, or when I have maximum compression. So that's saying a lot. This is a great visual, if I don't mind saying so myself. Let me just go through that again. Here's a relationship between position, velocity, and acceleration, PVA. Acceleration is at a maximum when the velocity is 0, which is an endpoint, and specifically it's when I have maximum compression. Or you could say, let's look over here at this max point at 2 pi. So let me just do x equals 2 pi. All right, so here I have a maximum acceleration once again when my velocity is equal to 0, and that occurs in this case at a maximum elongation. Maximum elongation there, maximum compression here. So if I go back to my visual, I can now safely say at this point, I have, for my acceleration, A equals A max. And this is A equals negative A max. Technically, I should have A equals negative A max based on what I just found out. And this is A equals A max. So, and this is A equals 0. Okay. So I have my maximum acceleration at these extreme endpoints. So what is the force? So number 9. Number 9 is asking you to find out the force at maximum displacement. So at x equals x max, based on this Desmos graph, which I think I need Desmos again. I just want to sanity check myself. Maximum acceleration occurs at zero velocity, which occurs at an extreme endpoint. So at maximum displacement, I have maximum acceleration. I can use that. At maximum displacement, I have maximum acceleration. And I need to start out my notes. Okay. So there. All right. At x equals x max, a equals a max. A equals a max. And you know what that means? Therefore, F equals ma. F equals ma, and so that means at x equals F equals ma at the maximum displacement, it's going to equal mass, which is 0.088 kilograms, times the acceleration, which turns out to be the maximum acceleration, which is given to us as 9,700 meters per second squared. So at the maximum compression or maximum elongation, here's the force acting on the particle, 0.088 times 9,700, or 853.6. 853.6 newtons. And this is the answer to part D, thanks to Newton's second law and getting our head screwed on straight with how PVA correlate in simple harmonic motion. The last part of this question says, what about at half its displacement? So number 10, F at x equals xm over 2. This is the dollar sign. When this red particle is right here at the halfway point, right here, halfway to its maximum value. So this is what I'm referring to as xm over 2. So I'm just going to use Hooke's law for this problem. So I have F equals, do I have a K? Is K given? No. All right, so F equals negative K times X. And did I not really figure out K? All right, so number 11. Omega squared equals K over M, which means K equals M omega squared. The mass is 0.088 kilograms. And omega squared is sitting there. Well, I never did store that. So, but here's omega squared, 9,700 meters per second squared, because right here, here's omega squared, all over 0.0096 meters. So this is going to give me my K value. I'll put that in memory location D. 0.088 just double checking, times omega squared times 9,700 divided by 0.0096, store alpha D. That's my K value. I'm going to just double check that. 0.088 times 9,700 divided by 0.0096. All right. So now let's finish this. Number 12 over here is, here's the new number 10. Number 10 now, I can say the force at that half displacement mark is going to equal, I'm going to drop the negative. That negative just means it's restorative. They just want the magnitude because they said they want magnitude. All right, equals K is sitting there in memory location D times half the maximum displacement. So that would be 0.0096 meters over 2. So let's do alpha D times 0.0096 divided by 2, or 426.8 newtons. That's the answer to part E. All right, so we're done with this problem. This one, I don't know, faster than I thought. A, B, C, D, E. That's it. Time check.
I'm sorry, Professor. Aren't we missing step C?
Say again?
Step C.
Step C. Yes, I knew it was too good to be true. Step C. Thank you for that. Okay. The good news is we got A through A, B, D, E. Step C, which is actually one of the better sub questions here. 12, 13. 13 says part C is what is its total mechanical energy? ME stands for mechanical energy. Mechanical energy is the sum of kinetic energy and potential energy. So what's the difference between mechanical energy and energy? Energy is kinetic energy plus potential energy plus non-conservative work, but we're ignoring non-conservative work here. Mechanical energy just focuses on the sum of kinetic energy and potential energy. So you know what? You know what I can say here? I can say the total mechanical energy. I'm going to go back to the bead. When this red bead, here's two ways of looking at it. When the red bead is at this extreme point right here, I don't have any kinetic energy. It's slowed to a stop. So kinetic energy equals 0, but my potential energy is the maximum value. Okay. If I wanted to look at my red bead right here at this point, at the halfway point, at this halfway point, it's sort of the flip. It's the flip side of that. At this midway point, kinetic energy is the maximum value, and the elastic potential energy equals 0. So you know what? You know what I'm going to do? I'm just going to say, and it doesn't matter, just half a dozen one, six another, but I'm going to say my mechanical energy, my total mechanical energy, if I look at maybe this point right here, if I look at the maximum compression point, okay, or that extreme point there, it's going to equal, K is going to equal 0. And the potential energy is whatever its maximum value is. And so that's going to equal 1/2 K XM squared equals 1/2 K. I just figured that out, didn't I? Where's K? Yes, it's in D. K is in memory location D. 1/2 K XM squared 0.0096 meters squared. So I'm going to do 0.5 times alpha D times 0.0096 squared, or 4.09 and some change. Joules. That's the answer to part C. Okay. All right, let's do this. Let's keep going. D, the maximum. Oh, what is the magnitude of the force on the particle when the particle is at its maximum displacement? All right, so let's do maximum displacement. Ooh, this is a chance to talk about some new stuff, I think. Let's see. Let's talk about this block again, bouncing back and forth. I'm going to go back. This is actually not a bad visual. This block right here is oscillating between max and min points. So I label this as the max point. Over here on this far left side, you know what? I can write it the same way. X equals X max. I'm not saying, you might say, why don't you say X min? And yeah, I can see why you would say X min, but amplitude is just basically saying, hey, what's the magnitude of the displacement with respect to the equilibrium point? This is the equilibrium point. Here I am at equilibrium, that midpoint between those two extremes, equilibrium. This is at this far point too. This is V equals 0, K equals 0, US equals US max. And you know, I'm going to add one other, A equals A max. This is where I have my peak right here at these extreme points right here at this far right point, or equivalently at this far left point. At these extreme points, when I have zero velocity, I have maximum acceleration. And the answer, why is that? Because right here, because of this expression for acceleration. Acceleration depends on the cosine of the motion, whereas the velocity depends on the sine. So those are always 90 degrees out of phase. Bottom line here, and you can plug in the numbers, but this is a lot of good information crammed into one pretty dense drawing. At this extreme point, I'm just being careful. That's my max displacement. Just like this is my max displacement way over here. No velocity, no velocity. That means no kinetic energy. That means maximum potential energy and maximum acceleration. That's going on at my extrema points, my maxima and minima point. A equals A max. Here, this is V equals V max, as I indicated. X equals 0. US equals 0. K equals K max. And A equals 0. So a great but sloppy yet busy visual, but that's all, I think a lot of it's in there. All right, so what is its maximum displacement? Or what is the magnitude of the force on the particle when the particle's at the maximum displacement? So 11 at X equals X max. A equals A max. Okay, so Newton's second law. Newton's second law says F equals MA equals 0.088 kilograms times my maximum acceleration, which is 9.7 E3 meters per second squared. And the calculator says 0.088 times 9,700. 853.6. Newtons. So that's D. And the real benefit of D is it basically nudged me to make sure I'm understanding what's the relationship between an oscillator's position and its displacement, velocity, acceleration, force, and energy. So this is a pretty dense problem. Last one. What about at half displacement? So when you read this, what is the magnitude of the force when the particle is at half its maximum displacement? If you just said, well, it's whatever, just take F max and divide by 2. And I don't know if I could give any credit for that, because I don't think that's there needs to be some justification. Why can you just divide the maximum force? You have to show, you have to provide analytical justification to show that that's valid, showing that that is valid. So let's just keep talking. Number 13, at max displacement at X equals XM over 2. So this is my way of saying when this oscillator is at half of its maximum displacement, I'm going to do this. I'm going to say, well, I know this. I know the amplitude, the velocity amplitude is going to be, well, let me do it like this. I'm going to do it like this. Actually, it's a new thought. I know the acceleration. The acceleration is going to equal from step 3 minus XM omega squared cosine of omega t plus phi equals negative 9,700 times meters per second squared, because this is collectively, this is A max. And they told you what A max was. That is provided. Cosine of omega t plus phi, and then number 13, number 14. At X equals XM over 2, cosine of omega t plus phi equals 1/2. So let's just talk about that. Here's a cosine function. This is X versus T. This is my maximum displacement, or I could say that's my maximum displacement. So this is my displacement amplitude. That's XM at that very peak or at this trough. And so this is 0. So this is the halfway point. Okay, I think that's airtight enough. This would be XM over 2. So I think that's enough justification. Maybe if I show that visual, but when this oscillator is at the halfway point, when it's halfway between right here, so right here, when it's halfway between X equals 0, which is this red dot, this is X equals 0, and its maximum XM, its maximum amplitude, it's right here, and this corresponds to cosine equals 1/2. All right, that's I think airtight enough. All right, so I would say therefore A max equals omega XM times 1/2. Actually, I'm not. Back up. So therefore A, number 14 again, A equals negative 9,700 meters per second squared times 1/2. F equals MA means F equals the mass point 0.088 kilograms times this 9,700 meters per second squared times 1/2. And then this is why you can simply calculate the force at this halfway point is the same as the max force divided by 2. Okay. Done. Newtons. Okay. It's pretty long-winded. So
Yeah, didn't you mention earlier that the force is equal to the spring, that the force is equal to the spring constant sign? This is or something like that. Well, I was just thinking the simpler way of it. Just if it's linear multiplication, then wouldn't that just mean half the distance equals half the force?
you're saying this, John. F equals minus kx.
Mm-hmm. If you half the k, it'd be half the force.
No, John, that's terribly incorrect. No, I'm kidding. I think you're right. So, right, it's linear related. So, F equals minus K times, well, this is what you're saying. You're saying, okay, if F equals KX, then you could say, well, that means F equals minus KX sub M, or F equals minus KX. Yeah, I think you're right. That is a much simpler way. That is a much simpler way of getting the same result. And there's nothing wrong with that. Normally I would say, well, yeah, but that's not quite the same. It is, that's a simpler and better approach. My only feeble claim to saving face is, well, at least you got a lot of conversation about this cosine function behavior. So, but had I thought about this, John, to be honest, if I had thought about this, I probably would have sidestepped this whole conversation. But now we actually have both. So that's good. That's good observations. All right. So thank you for that. You have a cube attached to a spring. And what I basically do, I'm going to walk up to this cube. So I'm literally going to walk up, grab that pink cube and twist it clockwise or counterclockwise. So I'll just say clockwise. I'm going to spin it. I'm going to rotate this pink cube 3 degrees and let it oscillate. It's attached to a spring after all, so it should start bouncing back and forth if I give it an initial amplitude. So let me, here, I'm going to maybe enlarge this a bit. Okay, so let me try. I'm going to walk up to this cube and I'm going to just grab hold and rotate it 3 degrees. That's my number. You might have a different number. Okay, so here's my attempt to show a 3 degree rotation. All right. So I'll exaggerate it. There's a certain amount of rotation here to there, and then okay. Okay. So this is my cube rotated 3 degrees, about that axis of rotation. Okay. So I'm gonna let me just put in some reference lines. So this is my axis of rotation. And there's my non-rotated position. So right to that attached point. And then here's my 3 degree rotation. I'm drawing it, obviously I'm drawing it at a greater than 3 degree, but just so it's easy to view. Oh, let's do this. Okay. And there's my attach point here. This is 3 degrees, even though, again, just to repeat, this is clearly more than 3 degrees, but whatever that is, that's my angular displacement. That's my initial angular, that's my twist. Okay. All right, so my spring is going to stretch. So here, I'm just going to represent the spring with just a solid line. So here's the spring right here. Just a straight, that's my spring length at that position. Here's my spring length. I'll give myself a different color. Here's my spring length to this position. Okay. All right. So that's the amount of stretch. So we need to figure out the period of the resulting SHM. So T equals $. That's what we're after here. What is the period of the resultant simple harmonic motion? Because when I let go, I'm going to grab this pink block, let go, and it's just going to bounce back and forth forever because there's no friction, there's no energy loss. So it's going to just tick tock, like kind of like a pendulum back and forth according to simple harmonic motion. All right. So now what's my plan of attack? And to be honest, I'm torn between two. Should I do force analysis or energy analysis? And I think both of these might be viable contenders. Torque analysis seems kind of like a natural because within force analysis, I would basically say sum of all torques equals rotational inertia times alpha. And I think this would work. And I also think energy analysis would work. I'm going to start with energy analysis. Energy analysis is usually my first consideration. If I'm not told, like if I'm not following a recipe, I'm always going to think in terms of energy balances, energy relationships. So I'm going to call this energy state A. Energy state A is when the pink block is at that halfway point. Energy state B is when that pink block has been rotated through that angle, theta. All right, so let's just talk about those energy states for a minute. So energy state A is when spring is unstretched, is uncompressed, and unelongated. In other words, when the spring is at equilibrium. I'm just writing this out just to be detailed. Energy state A right here is when the spring is at equilibrium. It's not compressed, it's not elongated, it's at equilibrium. And at that point, you know what, I can say a few other things here too. I'm going to say whatever omega is, omega at this point, omega at energy state A is going to equal its maximum value. So because it's going to, and this goes back to this view right here, Desmos, which I think I might have deleted it. Did I? Hang on. Oh, it's right here. Okay, this goes back to this reference. I know, I'm pretty smart now. I know the relationship between position, velocity, and acceleration for simple harmonic motion. So at maximum velocity, which is right here, this blue curve, at maximum velocity, my displacement is 0 and my acceleration is 0. So just remember, I mean, it makes that's a common sense thing to say, but even if you didn't have the common sense working for you, you still could figure it out graphically, one way or the other. All right, so that's energy state A. And then I guess I would say XA equals 0. The spring is neither compressed nor elongated. Energy state B, a few words about energy state B. Well, I could say this is when max spring elongation. If you wanted to, instead of rotating this clockwise, you could rotate it counterclockwise. And if you rotate it counterclockwise, I would be writing down max spring compression instead of elongation, but I don't think it matters. So let's see. Omega at energy state B equals 0. I don't have any kinetic energy. I have maximum potential energy. U at B equals its maximum value, U max. And you know, I better add that here. At A, this is UA equals 0. Okay. And I guess that's good. I could say, well, XB equals, here's XB. I'm going to have to draw it right here. Here's what XB looks like. This is the amount of spring elongation from, let me get, what's a good color? Orange. Here is XB. Ready, set, go. This orange line is the amount of spring elongation. This is what I'm calling X subscript B, the amount of spring elongation. So you know what I'm going to do? I'm going to use an approximation here. And this is a very common approximation. So here's what I'm talking about. Let me take a copy and paste. I'm going to copy that and that and that. Or not. Let me try that again. I'm going to use a birth of a radian approximation, and specifically, all right. So this is the radius. So here's what I'm saying. I'm saying when I rotate this pink block, this point right here, this green point kind of goes through this arc, goes along this arc. Goes along this arc. There, pretty good. Good enough. All right, so here's the arc. Here's the arc that this green point travels along this arc. So this is S for arc length. And you can see for really small angles, this arc length is pretty much, or is approximately equal to X sub B. So, that's, I think, good news. I'm going to use this approximation for, and this is a common approximation for small theta. For small theta, this arc length right here is going to be pretty close to X sub B, which is right here, X sub B. It's a little bit of an overestimate. So the arc length is in fact going to be a little bit longer than the actual spring elongation. But so anytime we use this approximation, we're going to have to think about, is this a valid approximation? So, but right now, let's run with it, and then we're not going to forget about studying this. But I'm going to do birth of a radian. Birth of a radian says the following. Did you know that radian measure is defined as S over R? So if that's the case, that's how I can say S equals R theta. And now let's personalize it. What is R? R is this right here. Here's R. This is the arc radius. That's R. This is R. If I look at my cube right here, I guess I'll just look at the pink cube instead of the purple outline. But if I look at the pink cube, this is what's happening. I've got, I'll just draw some reference lines. That's a good reference line. Here's a reference line. And then here's R. R is this value right here. This is the arc radius from my axis of rotation to that point there. Okay. So there's this is R. This is the R I have to find. I know this value is, this is D over 2. That value is D over 2. This value here is also D over 2. And I know because this is an isosceles an isosceles triangle, I know that if the two sides are D over 2, I know this is D over 2 times root 2. And if you wanted to do Pythagorean theorem to validate that, go ahead. But and it's good to be paranoid like that. But my arc radius is D over 2 root 2. So here's birth of a radian personalized for this situation. S is, I'm going to say X sub B, sorry, is approximately S, which is equal to R theta. So X subscript B is approximately equal to D over 2 root 2 times theta. I better use theta B. Okay. That's that. Here, this is saying the same. I'm gonna multiply this by root of 2 over 2. So X sub B equals D over root 2. That's my arc radius. And then you know what? I'm actually going to call this theta max. Because at energy state B, that theta is the largest value it's ever going to get. So this is theta max. Okay. All right. So that's the approximation I'm going to use. And for small angles, I mean, it is going to be pretty darn close. I'll be within that 2% margin of error, I'm pretty sure. But let's keep going with this. X sub B, now I have an expression for that. That's D over root 2 times theta max. Okay. Let's do energy analysis. Energy analysis says whatever energy I have at A plus whatever non-conservative work adds or steals energy, that's how much energy I have at B. And this quickly becomes, there's no non-conservative work going on. So I have the kinetic energy at A plus elastic potential energy, just double checking, at A equals my kinetic energy at B plus my elastic potential energy at B. Let's personalize this. So let's see at energy state A. Well, here, 1/2 I omega A squared. It's not, why am I not writing 1/2 mv squared? Because there's no linear motion. 1/2 mv squared is translational kinetic energy. 1/2 I omega squared is rotational kinetic energy. And this is pure rotation. It's not translation. It's not a combination of both. So this is my kinetic energy at A, which is that halfway point. I don't have any elastic potential energy at A because the spring is completely relaxed. At B, which is this extreme point here, this maximum displacement, I don't have any kinetic energy, but I do have elastic potential energy, 1/2 K XB squared. So all of a sudden, this just looks a lot easier. This is my kinetic energy at A. This is my potential energy at A. This is my kinetic energy at B and my potential energy at B. Some low-hanging fruit, the 1/2s go away. 1/2 here. So I'm still not seeing my dollar sign, but I know enough that if I'm just going to go down this path of energy analysis and hopefully my dollar sign will appear as if by magic. So I have I omega A squared equals K times XB squared. Okay, let's go with this number 6. Let's look at omega A. Again, omega A, remember, omega A is the maximum angular velocity. Let's just check. Let's get a visual confirmation. So at A, when this pink block is at position A, it's at the halfway point. So it's at its peak velocity at that halfway mark, because remember, this is going to continue to rotate past that point to some, to 3 degrees on the other side. Okay. So I'm going to do birth of a radian yet again. I know S equals R theta, generically speaking. And if I divide by time, I know V equals R omega. So now if I need to capture the maximum velocities, the maximum linear velocity is related to the maximum angular velocity by that arc radius, like that. But to get even more personalized, the maximum velocity equals the arc radius, which is d over root 2 times the maximum angular velocity. And that's the substitution I'm going to go with. I'm going to go with omega m. The maximum angular velocity is going to equal the maximum velocity all over this, the arc radius. Okay, but wait, so 7, 8, 9, 10, 11, 12, aha. More revelations. Again, the great thing about being an engineer is you have to be logical and imaginative, and both of those are always kind of in play. So here's the imaginative part. Aha. I don't know how imaginative this is really, but the maximum velocity is going to equal omega, simple harmonic motion, times xm. Okay, this comes from back here. I just have to go back to one of these previous problems. Where did I start? Where's the first time I blurted out maximum? Right here, for example. So there's maximum, and I went through the deep dive. I went into the deep dive about where this comes from. So hopefully that sunk in. But my velocity amplitude is omega x sub m. However, I need to be careful with subscripts. That's why I added this subscript right here, that it's omega. It's the simple harmonic motion omega. It's angular frequency as opposed to angular velocity, which I know you got to really keep thinking on this. Otherwise, you're going to get confused. But I'm just going to note this omega is referred to as angular frequency, or I'm just calling it simple harmonic motion omega. That's not the same. It is not equal to omega max. Those are two different things. Okay, so number 13. Number 13, let's update number 5. So here's the new number 5. I have I times omega A. So after all of this conversation, omega A equals, I didn't quite finish that. So here, let me erase that. I need to finish my train of thought here. Number 13. Number 13. Okay. So omega max, that maximum angular velocity, not to be confused with angular frequency, is Vm. Here's Vm. Omega SHM times xm all over my arc radius, d over root 2. Great success. Let me let me clear some clutter. Okay, step 14. Now I can go back to number 5. So here's my updated version of number 5. I times omega a squared. And again, remember, all of this also equaled omega a. See step 6 and even step 1. All right, so I need to square that. All right, I got to square this whole expression. So I have I times omega SHM times XM all over D over root 2. This whole thing squared equals K. Again, I'm just looking back and forth at equation 5 equals K XB squared. All right, so now I think it's just pretty straightforward rearrange. Well, there will be some interesting points here. Let's see. So I have I omega SHM squared XM squared. That's my numerator. My denominator is going to be D squared over 2. All of that equals K XB squared. Okay, and XB, and I better add this. XB is also equal to X max, which I just erased that visual. But XB right here, this is the maximum elongation, what I'm highlighting here. This maximum elongation or this maximum stretch is that's XB. All right, so that's why I'm saying X sub B is the same as X max. So I'll just say, all right, these are the same. X max here is the same as XB. Okay, so let's keep going. There's the dollar sign's hiding in here somewhere. All right, so now number 16. Here's the dollar sign. The dollar sign is, I'm going to keep going with this. I'm going to isolate omega SHM squared. Because there's the dollar sign is hiding in there. Omega SHM squared equals K times D squared over 2. All of that over I. Okay, so now the question becomes, what's I? And the answer is, well, it's for a cube. And you'll have a lookup table and you'll see for a cube, you remember that the rotational inertia for a disk was 1/2 mr squared. The rotational inertia for a ring was mr squared. It depends if it's this. Well, for a rod, the rotational inertia for a rod was 1/12 ml squared. The rotational inertia for a point is just mr squared. And the rotational inertia for a cube, C for cube, is 1/6 md squared. So I didn't do like all of the differential calculus in 2 seconds to come up with that conclusion. I'm saying that's what a table of rotational inertia spits out. All right, so number 17. WSHM squared. Let me back up. Let me miss more space. Okay. W omega SHM squared equals K times D squared over 2 over I, and I is 1/6 md squared. So let's simplify that. That's going to equal the d's cancel, d squared cancels. That's good news. This, come on. This d squared cancels with this d squared. So I am left with 3k over m. Right? Right. Okay. Interesting, because look how similar that looks like. We had omega for a simple spring mass system. Omega squared was given as k over m. This is not a simple spring mass system. It's a spring cube system. So it's not we don't have omega squared equals km. That's simple spring mass. We have omega squared equals 3k over m, unless I'm forgetting something. Well, we'll find out. I can't see anything I'm forgetting. All right, so, but here's omega SHM. Omega SHM is 2 pi over t. That is omega SHM, because as always, omega is 2 pi over t, right? As far as simple harmonic motion is concerned. That's why, again, this is angular frequency, all right, not angular velocity. All right, so I need to square that, and that's going to equal 3k over m. So now your job is to solve for t. When you solve for t, you're going to answer the question, how long does it take this cube to make one bounce, to complete one bounce? So let's figure that out. Doing okay. They gave us a spring stiffness constant, I'm hoping. The spring constant, yeah, they did, 1150. Did they give us the mass? They did, 2.9. All right. Zero 0.182.166. Interesting. So I think, well, yeah, seconds. Interesting that the approximation I used actually kind of dropped out. 668379. Yeah, okay. So my calculator actually matches exactly with Wiley Plus. Maybe they ended up using the same approximation I did. Okay. What a great problem. And that's 1, 2, 3, 4, 5, 6 quizzes is probably enough for one day. Okay. So you guys, before I sign off, I'll put the screen back up, but let's just bring up here. I'm assuming you're good to go. Otherwise, speak up. And if not, if everyone's good, then I will see you guys Thursday at 1 o'clock. All righty then. See you Thursday at 1 o'clock.